Thank you. My name is Mohan. I'm from the School of Computer Science at the University of Birmingham. I'm an academic here, and I'm going to talk about an architecture for explainable reasoning and learning in robotics. And thanks for this opportunity to speak to this audience. I really like this audience. I've been here once before, so let's get started. And before I start, I should acknowledge that the work that I'm talking about here is work that's been done over several years with collaborators. Main collaborators are listed at the bottom, and also grateful to the funding received from different funding agencies, which has made this possible. Okay, I shouldn't forget to do that at the end, so let me do it at the beginning. Let's get started. So what are some of the questions that has driven this line of work? Is basically these are the questions so we set out to answer. First, how best to enable robots to represent and reason with different descriptions of incomplete domain knowledge and uncertainty. And for much of this work, I'm talking about common sense knowledge and different descriptions, some of which is like, default statements, which we will translate later, for instance, to logic, like books or textbooks are usually in the library, or cereal boxes are usually in the kitchen. And at the same time, there are other kinds of statements that, because we deal with robots, they come from sensors, and we typically tend to use probabilistic models for them. So you could say something like, I'm 90% certain the book is in the library. So the second question says, because this knowledge is incomplete and it's associated with different degrees of uncertainty, how do you enable robots to learn interactively and cumulatively from different inputs, like sensors or from humans, right? So here specifically, we talk about, when I say learning in this talk, I talk about the robot learning about new actions, new action capabilities, and domain dynamics. That is, things about actions and change in the domain, right? So for instance, a robot with a weak arm can't lift a heavy box, for instance. And the third basic question, which sometimes proves to be really hard, is how best to enable designers to understand the robot's behavior and establish that it satisfies certain desirable properties, right? And here you could think of formal methods and other things as well. For the purpose of this talk, this is probably the important question, because we will talk about things like explanations, what are the agents or the robot's intentions, and hypothetical questions like what would happen if the robot were to drop something on some other object, and so on. Okay, so before I get into the actual methods, I want to spend a couple of slides talking about the inspiration and the core ideas. So the basic ideas and the assumptions that we make, I want to lay them out first. So the inspiration here is that from cognitive systems. So it's a cognitive systems inspired approach. So what that is will hopefully be clear shortly. So, and this is also inspired by lessons learned in human behavior and human cognition and control. So we're not saying that this is how a human does it, but we are saying that these are the kind of behaviors like humans seem to exhibit, and we want to try and create similar behavior in our robots or our computational systems. And in our case, we represent, reason, and learn jointly at different abstractions. There can be different schemes. They don't all need to use the same unified representation by any chance. That's not required. But what we require is there needs to be a nice coupling, a formal coupling between the different abstractions that they use. And there should also be some nice ways to connect between the different schemes. So they could reason with different schemes at different abstractions, but there is a nice link between them. And I will show some examples shortly. So you could imagine, if you will, that inside the robot sits a logician, a statistician, and a creative explorer. They may not work well together in the real world, hey, but they work well inside our robots, right? So there are these entities which are going to talk to each other. So we're going to combine this kind of knowledge-based reasoning and data-driven learning, and I'll show examples. And we want the robot to learn interactively and cumulatively. That is, as we get more and more data, we don't want the robot to get slower. It has to somehow crystallize these more concrete concepts such that it makes the best use of the information it has. The last bit, because we're talking about explanations for us, for this talk and for the work that I'm talking about, explanations are relational descriptions of decisions, beliefs, and as I will say later, the robot's experiences as well, right? And we want to be able to answer different kinds of questions, like descriptive questions, contrastive ones, counterfactual ones. And woven in between all this is this notion of cause and effect, which hopefully will also be clear later. Okay. So in terms of claims, we claim that there is a distributed representation of knowledge. It can be common sense, it can be specifically probabilistic or otherwise, but it is a different abstractions that are coupled with each other. And there is a clear separation of concerns. This is all the more important in robotics, where there is a domain-specific and domain-independent component. And what this does is this gives you a common methodology. So I could put the same thing on a different robot, and we have done that, or even on a different system that operates in a dynamic domain. And there should be only certain components which you can still follow a common methodology to change, but everything else should work unchanged. That's what we are trying to go towards. And the knowledge elements that we have should support non-monotonic revision. You should be able to revise previously held conclusions. Of course, for something like robotics, this makes absolute sense. And the last bit is we do this kind of here and there reasoning, where we use a combination of satisfiability and stochastic policies to both think about here and there in space and in time. And as examples of domains, what we have been using and what I will talk about is kind of this assistive robot that does a variety of planning, scene understanding, and manipulation tasks in different things, in simple tabletop domains, in a full-fledged map of an entire floor, or even in simulation, right? And we will look at some examples of this shortly. So before I can get to the explanation part, I have to give you a layout of what goes on in the representation, reasoning, and learning. So I'm going to spend some little time doing that next. So as a very coarse, I shouldn't use the word coarse, very high level, or even that is wrong, a block diagram of the architecture is probably the right way to describe this. So you could think of there being just two resolutions here, and they're labeled I and I+1. And when we get to explanations, we will see others as well. And you could say that there is a coarser resolution description of the world. The robot could, for instance, think about rooms and corridors in a building on a particular floor. And it creates a sort of more, given a particular goal, it creates using non-monotonic logical reasoning. It creates a plan of abstract actions. Now, what happens is that for each such abstract action, it automatically jumps to the lower resolution and is able to figure out what part of the lower resolution domain is relevant. And there it reasons probabilistically at a finer granularity, right? It now creates for each abstract action or an abstract transition, it creates a sequence of one or more actions at a finer granularity to achieve it. And at the same time, because this knowledge is incomplete, every once in a while it goes around exploring either as a result of some failure or just because it can get more information, it explores and adds more knowledge to the existing system. So to do so, we explored the complementary strengths of non-monotonic logical reasoning, probabilistic reasoning, and different kinds of learning paradigms. We are not particular about one. I will talk about all of these in some form, deep reinforcement learning and inductive learning and other forms. If you're more interested to know more, there are papers to look at. So let's start with a simple example, right? So let's start with the action language description of the world. So we have the system description, which consists of a sorted signature and some axioms in this action language. And we have basically some statics, like a place being next to another place. And to this audience, I don't need to explain what these are. You can have a location of a thing that maps a thing to a place. And you also have a Boolean description of whether a robot has a particular object in hand. So these are fluents. The next two is a static. And then you have actions, which basically you can have things like the robot can move to a place, the robot can pick up an object. There are, of course, others. And there are also exogenous actions that are not done by the robot, but it uses in explanations. But I'm skipping that for now. And the last bit is the axioms, right? So the axioms here are, because we use ALT, it allowed three types of them: causal laws, state constraints, and executability conditions. So for instance, you could say that if a robot rob1 moves to a particular place or it executes that action, at the end of this action, it causes the location of the robot to be that place. The second one basically says that if a robot has an object in hand, then the robot and the object have to be in the same place. It's a constraint. The third one basically says if the object and the robot are not in the same location, hey, the robot can pick it up, right? So that's your executability condition. Okay, so then the other component, of course, is the history, which contains a record of past observations and actions, right? What actions happened and what observations of fluents being true or false did the robot observe at particular time steps. We expand this to include initial state defaults, where you can say that initially, I believe the textbooks are typically in the library, and we provide means for the robot to recover from any such errors that come later when the defaults are not met. So whenever there are unexpected successes and failures, you want the robot to still persist and not procrastinate and try to achieve its goal. So I will not talk about this here, but we also have this additional component where it can also think about the notions of intentions and create a notion of intention and use that to think at the level of mental fluence and actions, right? So this is all captured in the coarser resolution. Now, from this coarser resolution, we have to be able to, from the representation, we should be able to reason. And to reason, if it was not clear to you already from some of the syntax you've seen before, we translate this to an answer set prolog program. It is translated automatically. And then you reason by computing answer sets. And of course, we know in this audience, again, this notion of non-monotonic logical reasoning. And it supports these nice concepts of default negation and epistemic disjunction. So the agent only believes that which it is forced to believe. So things being NOTL does not mean that it's false. It's just that it's not believed to be true. Right? So as the input for a planning task, the robot would receive the system description and the history and a particular goal. And at the course resolution, it would output as a plan a sequence of abstract transitions, and it will take each transition from one sigma 1 to sigma 2 with a course resolution action and try to execute this, right? And of course, this whole thing is done with, as I said, Prolog at this level. Now I'm given this transition and I have to find ways to execute this. Of course, this is not directly executable by a robot. There is still no sense of actually reasoning about noisy observations. And of course, this is at a level at which the robot can't execute, right? To do that, we have this notion of refinement, which formally links the transition diagrams at the different resolutions. So for any given course resolution description, you can create a fine resolution refinement by following a fixed sequence of steps. And here you can also introduce this notion of theory of observations and other specific things if you want. And the details are in papers. But the key thing is this formal relationship, right? So for given any given transition to the course resolution, you are given this magical knob that does two things. One, it automatically transitions you to the finer granularity representation. And second magical superpower, it basically gives you this kind of this red rectangle that you see in this figure, which says that you don't need to reason about the whole finer granularity description. For the transition that you care about, this is the only region that matters in the finer granularity, right? And this is what we call zooming. And once you do this, you can also introduce, if you had probabilistic descriptions of uncertainty, you can easily introduce them here. And then you can use different probabilistic sequential decision-making schemes to implement this. And we have done different things in different papers, like, depending on what assumptions you're willing to make. And so I just list some of them here. But the key thing is the outcome after a sequence of final granularity actions will be either a success or failure and some observations. That gets sent back to the course resolution. Because that's a nice coupling, you can automatically translate from the finer granularity back to the coarser granularity as well, and then you can continue, right? So this is what happens in terms of basic representation and reason, right? Okay, now a quick diversion, short one, to the learning aspect, right? So what we did is we said, okay, what are the, if you look at the kind of problems we are looking at in robotics, oftentimes the key state of the art is based on deep network architectures these days. But of course, they have the standard well-known limitations that they require large labeled data sets and considerable computational resources. And the internal representations and mechanisms are often very difficult to interpret. Right? There is a lot of excellent work going on, but still, it's still largely a black box system. So then we said, okay, we care about knowing what the system is doing. So can we take inspiration from, again, from the cognitive systems? And we are already representing and reasoning jointly. So can we also start learning and have them inform and guide each other, such that learning is driven by the reasoning, and learning gives back knowledge to the reasoning system. And we want to achieve scalability by once again looking at notions of abstraction and what is relevant and what needs to persist over time. And the experimental domains, as stated before, we look at scene understanding problems as one example here. Think about occlusion of objects and stability of object structures in a scene. Like I'm looking at a scene of objects, and I want to see if their objects are occluded from each other, and if their structures that are stacked there are stable. And this is related to a classic benchmark problem in computer vision of VQA, which is visual question answering explanatory questions about the scene. And we would like to do so with limited data. So again, sort of high level description. Remember that our goal here is to use KR tools for transparency in reasoning and learning. Explanations to us are relational descriptions of decisions, beliefs, and experiences in terms of the attributes of the domain, attribute of the agent, and the actions that are taking place. And we want to provide contextual and relevant information on demand. And in order to do so, we characterize explanations on the basis of a few axes in terms of abstraction, in terms of specificity and verbosity. And we provide a methodology that takes this axis to characterize explanations. And to us, then, a good explanation is that which conveys the necessary information. So this is interactive, and this depends on the context, and it depends on the person that the robot is interacting with. And what we want to do is we want to exploit the complementary strengths of non-monotonic logical reasoning as before, the probabilistic reasoning as before. And in the example I will show now, I will talk about deep learning, right, as the learning system. Okay, so let's take these images that you see at the bottom. These are basically objects stacked in both real world and in simulation. And we have these images of objects and scenes. And let us say I'm giving you a small labeled training set of objects being occluded, or about the stability of structures, saying that, okay, in the middle scene, the structure with the blue, orange, and red blocks is stable, for instance, right? And if I put a sort of ball on top of it, of course, it would be unstable. And I can also give you some basic answers to some questions, and that will be clear shortly, right? So I give you this RGB or RGBD with a depth image in a robot context from a robot capturing an image of a scene, and I give you some labels in a training phase. What would traditionally happen? Traditionally, what would happen? I mean, I shouldn't even say traditionally. In the current state of the art, what would happen is some deep learning system would be constructed, and you would take this image, you would take the outputs that you're given as labels, and you would try to create the mapping between input to output, right? You would extract some features, and then you would either give me the outcome in terms of stability and occlusion, or you would give me a description in terms of what is in the scene as an answer to my question, right? So all this would be done with this black box system. So we instead say, okay, no, we don't have to do that. Let's try to do something different, right? Let's try to use whatever knowledge we have and simplify this process. How can we get reasoning to inform and guide our learning, right? So first thing we do is we look at some basic features that are relevant in these kind of problems, like spatial relations between objects. And you could also add other things as we have done in other work, like color, shape, size of objects, and other features if you have them. Now, what we do is, because these things cannot all be specified in advance in all but the trivial domains in robotics, we have incremental grounding of these propositional words that describe these spatial relations. And this is something the robot learns on the fly. And then what we do is we say, okay, I have some basic knowledge about the domain. I don't start with a blank slate. In fact, contrary to what some deep learning systems say, there is no end-to-end learning system. You have to provide some structure, otherwise learning can't happen. So in our case, what we do is we reason with the extracted features, and we reason with some of the rules that we already had about the domain. Like for instance, we are basically saying that in the second rule that you see here, that if an object O1 is below another object O2 and it holds at a particular time step, then the robot can't pick up object 1 because it is below another object. So it's not allowed. It can't do a pickup action, right? So certain basic things you can think about and say that, okay, these objects are occluded or not, or these objects are stable, object structures are stable or not. And if such answers are found, I don't do any learning. It's not relevant here. It's a very simple idea, actually. And then what we do is we say that when I'm not able to give you an answer, or when I give you an incorrect answer on a training data set, that is when I say, okay, so now I want to learn, but I don't want to learn with the entire image or the entire image data set. Instead, I use my knowledge of the domain in the form of this encoded rules and whatever prior knowledge I have to automatically extract for you particular regions of particular images on which you're going to do the learning. Everything else I leave untouched. I say, no, that's not required. I can already handle that with the knowledge I have. Sort of like, if my existing knowledge is sufficient to deal with these questions I'm posed, I don't see a point, as in like, the robot says, I don't see the point of learning anything now. So, but when it has to learn, it has a focused learning mechanism. And we find, not surprisingly, that even though it's a small data set, it's a focused learning problem. So it learns both faster, and it's also more reliable than learning with the entire data set. So then what it does is it produces the output labels, and we can use the system now to produce both the output labels of occlusion or stability. And we can also have it provide with other deep network structures like LSTMs. It can also provide you with answers to questions, right? But we don't stop there. We say that whenever I have to use learning, I'm also accepting that my knowledge was not sufficient. Either there was something there that was incorrect, or it was incomplete, right? So what we then say is, can I now learn something that captures the behavior again, not the internal operation completely, but the behavior of this deep network system, such that it provides the description that was previously missing. And to do that, we basically take the same image regions that were used to train the deep learning system, and we pass it through an inductive learning scheme based on decision trees and other such simple structures. And from there, what we do is we extract simple constraints, causal laws, and so on. And once again, I'm not trying to completely explain what's going on inside the deep learning system. That's not the objective. Instead, I'm trying to explain the behavior on the basis of these new axioms that I have learned. And then I output these new axioms and I merge them nicely with the existing axioms that are already there, so that I correct any errors that are there in my reasoning system, and I can continue. So the next time around, I won't make the same kind of mistakes, or I will provide correct answers when I'm provided with similar scenes and ask similar questions. Okay. So as an example, these are the kind of decision trees a robot might, and this is a very small subset of a larger tree, just for illustrative purpose here. So for instance, if you were to go down the top branch, basically you are saying that if object A is above object B and B has a regular surface, then A is not stable, right? So then from there, you can come up with a particular rule, which basically says that, okay, an object A is above object B, B is irregular, and A is not stable, right? So it's basically a rule that comes from there. So what we are essentially saying is the decision tree here is based on the relational structures that are already there in the knowledge base that are used for reasoning and that are also used for learning, right? So what I'm trying to point out is the underlying representation is what is being used for all structures. And as a result of which, what we are able to do is we are able to also produce new axioms that can be merged with existing ones.
Okay. Mohan, yep. 4 minutes, 4.5 minutes left.
Yeah, I'm almost done. I'm going to the actual explanation,
Good
examples. Okay. So, and this is just a high-level overview. What we are doing essentially here is providing relational descriptions. We are able to construct answers to different kinds of questions that are descriptive, contrastive, or counterfactual. And we're able to talk about decisions, beliefs, and explanations. And the key thing here, once again, is it's able to automatically extract the relevant information from your knowledge base on the fly to provide the answers. And if something is ambiguous, it's also able to automatically construct disambiguating questions to the humans to interactively figure out what exactly the human wants. And this is again a kind of a tree that it does automatic belief tracing for a particular question to go back or forward in space and time to talk about and figure out what exactly is the correct explanation. Okay, let's look at some examples before we stop. So first one is if you're given a goal of a cup has to be in the office and you have the default knowledge that cups are usually in the kitchen, then the plan would be that the robot moves to the kitchen, grasps the cup, comes back to the office and puts it down. And now each such action that you have here has to be executed probabilistically and just showing you the relational statements that are there instead. And in the end, the robot succeeds. And if it's not able to succeed and it fails, then it basically learns rules of the form that if I try to grasp an object, but if the object is heavy and I have a particular kind of arm, hey, I can't do it. So I will know not to do so in the future. Okay, and in terms of the explanations, let's take this image on the left that the robot's camera is capturing. And then we ask the question, basically ask the robot to say, put the red block on top of the orange block. And a plan would be move the blue block to the ground, move the orange block to the ground, and then move the red block on top of the orange block. This is a reasonable plan. But now the human can ask, why did you pick up the blue block first? The Baxter robot, which is can say, oh, I had to pick up the red block and it was below the blue block. So that's why I had to pick up the blue block first, right? And then the human can ask, oh, as a sort of other option, right? Contrasting, why did you not pick up the orange block first? So it can say, okay, because the blue block was on the orange block, I can't do that. And so underneath that, it's doing different kinds of reasoning in order to be able to answer this question. You can also ask, a human can ask hypothetical questions. Human can say, oh, what would happen if I push the ball? So it can now project again in different points in space and time and say, okay, if you push the ball, it's going to collide with the structure. And the answer in this case would be that the structure would topple, right? So it can give you answers to those as well. And just a quick shot that like a snapshot saying that though I talk about this in at a particular abstraction, it can easily weave in and out. And it's able to do weave in and out, not because of some fundamentally new algorithm, but basically because we exploited this notion of abstraction and the coupling between the transition diagrams. So for instance, you can describe the plan and then say, okay, I want a more detailed description. So it can automatically transition to a more finer granularity description and pick out things for the essentially same facts, but at a finer granularity. And again, you can ask questions about beliefs or experiences and so on. Just let me show you this as in terms of the deep network structure itself. So on the left, you see this blue and red plots, and the blue plot is basically us. The red plot is the state of the art, so to speak, with a deep network structure. On the x-axis are the number of training images, and on the y-axis is accuracy. So larger numbers are better. And as you can see that for any given accuracy, that a horizontal line, the blue curve gets there with a much smaller number of examples than the red curve. And this is even for toy examples. For other cases, it becomes more prominent or pronounced, like the bottom right graph here. This is answering questions based on limited images. The blue curve is again the state-of-the-art system. On the x-axis is the number of training images. You can see that even with very small number of training images, you get a really high accuracy with our system, which is the orange bars. Okay, so I'm going to wind down the talk now by just saying that we can also do the same for different kinds of plans, not just for the learning system, but also the reasoning system. You can start initially with this image. You can move this red block as a target. You have to move it somewhere else. You can initially start with a large number of plans. Many of them are incorrect and suboptimal. But as you keep learning over time, you are able to produce much better plans, which are all correct. And you're also able to do so in different kinds of domains and provide explanations for all this. Okay, so the last slide here is essentially that if you combine this learning and reasoning and also weave in the explanations, the table that you see at the bottom, basically it says that without the learning, you initially for different kinds of questions, you might have slightly lower precision and lower recall. But as soon as you combine it with learning over time, you are able to even get the previously unknown knowledge, and you're able to provide much better explanations, and you're able to provide the correct explanations. In this case, correct again is defined by what is required in that particular case by the question that's being posed, and the ground truth in this case of what is a good explanation is retrieving the correct literals that are required, right? And even if you retrieve extra literals, that is considered wrong, which is why you have these high numbers, but they are not 100%. They're not wrong. They're just giving you additional information that is not required. Okay, last slide. So in terms of contribution, we provided this notion of stepwise refinement that simplifies design and implementation. It increases confidence in the behavior of the robot and promotes scalability. There's a clear separation of concerns, which helps us take the same architecture and move to different domains. With the robot inside the robotics field, we are able to combine non-monotonic logical reasoning, probabilistic reasoning, and different forms of learning to inform and guide each other. We are able to provide interactive explanations on demand at the desired abstraction. And we provide the designer with a predefined set of steps that the designer has to follow. Other steps or other parts are automated. I will stop here and take any questions. Thank you for the opportunity.